Hello, I'm Matthew Schofield, and with my group mates Alex Lamb and Dylan Shapiro, we created the application EqSolv. Our main objective was to create an application that uses machine learning to identify handwritten math expressions and solve them. We support the symbols 0 through 9, as well as parentheses, plus, minus, multiplication as an X, and division as a /. We took many images of equations and then individually labeled each symbol. We then used object detection model architectures from TensorFlow's Model Zoo, and these architectures have been designed around common objects in context. So having the symbol objects in the context of equations is similar. We then developed a semi-supervised dataset generation technique to expand upon our training data. Lastly, we present our solver by creating a program around it that can be launched as a website or an application. Some background on TensorFlow's object detection is that it's supported by Google Research, and again, it mostly focuses on the COCO dataset, which is a large-scale object detection, segmentation, and captioning dataset. These two images are from TensorFlow Research's object detection GitHub with examples. So, our model architecture is an expansion upon an earlier RCNN. This is a region-based convolutional neural network. First, it uses selective search to propose regions. It does this by scanning an image and grouping portions based on color, texture, and size. Once regions are proposed, a CNN acts as a feature extractor for a proposed region, and then an SVM classifies a region's feature map as to what object it most likely is, as well as outputting offset values for adjusting the bounding boxes around a region or object. And below is a diagram. Our model utilizes the faster RCNN, and this architecture was developed as a way to speed up the RCNN, as RCNNs alone are very slow, sometimes taking almost a minute to process an image, while the faster RCNN can work in video streams. So, the faster RCNN, instead of selective search, uses a CNN as well to propose regions. And as well as proposing each region, it proposes each region with an objectness score, which is how likely a region is to contain an object. Not any specific object, just an object of interest in general. If it's likely that a region contains an object generally, then that region is passed to another CNN, which predicts the object's class and any bounding box adjustments to the region. So, our dataset. These are handwritten images of mathematical expressions that we collected from friends and family, and we put these on the mediums of marker on whiteboard and pencil or pen on paper. To label our dataset, we use the application label image, where you can load a directory of images and then draw bounding boxes around each around each symbol within an image, and then label each bounding box as to what symbol it contains, as shown below. We also developed a semi-supervised technique, which is somewhat common, though we take our labeled images into validation and training sets initially, and we create a model. Then we have unlabeled images, which we give to the model, and the model, if it correctly labels an image, then a human moderator can approve this and add the correctly labeled image to the training set. Otherwise, an incorrectly labeled image should be returned to the unlabeled set, and as iterations continue, hopefully it too will be correctly labeled. Our data set is laid out, with most of the images being in the training set. We also have a validation set to ensure the model's accuracy, and lastly, a test set, which we will show evaluations of. As far as frequency of each symbol within our dataset, we see that each symbol is represented, though there are some biases towards plus, minus, and 1 and 3. Plus and minus were the first operators that we used, so naturally we have a lot of extra images, as we did not implement multiplication, division, parentheses until later. And 1 and 3's overrepresentation and frequency is perhaps just a bias in randomly writing digits. We performed an analysis to find what an average of any given symbol looks like by creating each image as a matrix and then taking the submatrix of each symbol. So we have shown a 5, 3, and plus, and this was useful that we noticed that 2 had 2 distinct symbols, where there was a 2 with a loop and then a more regular 2. So we split these into different classes. The model outputs a list of classes, boxes, and scores. The boxes are the 4 normalized coordinates as the xy minimum and xy maximum. And these scores are how likely a bounding box is to contain a corresponding class. If the score is above a certain threshold, in our case 75, we then take the class and based on its location of its bounding box, we organize the approved classes into a string, which we then use Python to evaluate. In training, the model architecture uses a loss function that combines 4 sub-loss functions. That is how well the CNN that classifies the boxes and localizes the boxes bounding, and as well how well the region proposal network, which is the earlier CNN, localizes a region to an object, and how well it predicts how likely a region is to have an object. As far as our final evaluation, to better understand, we took a directory of 100 test images, and we found the ratio of how many equation images were correctly solved. We compared our model with the app Photomath, which is popular for solving handwritten mathematical equations. Version 1 of our model operates as described on the previous slides, and version 2 adds the extra feature of logic regarding parentheses. We noticed our model sometimes would confuse parentheses open and close, so we added the logic if there are 2 open parentheses, it's likely the later is actually a closed parenthesis, and we make that adjustment. We also did an evaluation by medium, and we found that paper was underrepresented in our train set, and that showed in testing, and that our models actually outperform its commercial counterpart in Photomath using the marker medium. Our application can be hosted as a website or either locally or deployed to the cloud. A user can upload an image of an equation and our application will solve it. Here are 2 examples of uploaded images, how it boxed them, and then how it solved. We also abstracted our toolchain by combining a tutorial that had multiple scripts and parameters and directories being used into a single script and a few directories. So we will be posting this to GitHub, and you too can create your own custom object detection applications. Please reach out to us if you'd like any help. Here are the GitHubs where we will be posting our equation solver application and our object detection creator pipeline. Here are additional acknowledgments as far as TensorFlow's object detection, the faster RCNN paper, and 2 tutorials that helped us gain an understanding. Thank you.